Okay, chapter 15. We have now crossed the great divide out of equilibrium, thermodynamics, and stat mech, and are entering into a new major section of the class, chemical kinetics. Unlike thermodynamics, which deals only with time-independent, eternal equilibrium states, chemical kinetics deals with how fast things go, with how things change with time. And it is at least as important, well, about as important as thermodynamics. The two together, chemical kinetics and thermodynamics, stat mech, provide probably the most powerful and most common and most widely used ways of understanding pretty much any chemical system that there is right now. And I don't think that'll ever change, honestly. The two are just so incredibly powerful for understanding every chemical system that I think that will still be true 1,000 years from now. All right. One of the things about chemical kinetics that is new, among many others, but maybe one of the more fundamental things, is that whereas equilibrium stuff like that, like thermo and stat mech, only tell you about the beginning state, the equilibrium state to begin with, and the equilibrium state that you end at, kinetics gives you the whole progress of reaction. And in fact, we'll set up equations, we'll solve those equations, which give the concentrations of reactants and products, everything involved in the reaction, in fact, as a function of time at every moment in time along the whole process. That means that in a lot of ways, kinetics is more complicated than thermo. In some ways, it's not. It just depends on exactly what you mean. But it means that we'll be doing some new kinds of things now. We'll be solving differential equations and the like. We'll be analyzing fairly complicated systems of differential equations. And that requires a new bit of thinking and a little bit more complicated way of thinking in some cases than what we've done so far. Before we go on to chemical kinetics, let me just say, as an aside, that chemical kinetics is one small part or example of a much broader and very deep and beautiful and complicated and subtle field that's called non-equilibrium statistical mechanics. All the stat mech that we've done so far has been equilibrium statistical mechanics. It deals only with the statistical distributions and probabilities that occur when you're at equilibrium. If you go away from equilibrium, all those results we've talked about so far are no longer right. But there is a field, a large field, as I say, that deals with what happens when you do go away from equilibrium, and that's non-equilibrium statistical mechanics. It has many branches, it's broad and it's complex. Chemical kinetics is one small part of that. It's a very powerful and important part, especially for chemists, but it is only one small part of it, and one of the simpler parts of it too. So in the future, you will probably encounter non-equilibrium stat mech in some form or another. Undoubtedly you will if you stay in any kind of research-related field anyway. And you should know the name. You should know that it exists out here. We won't be able to talk about it this semester. There's just too many other topics that are more basic that we have to cover, but you will encounter it out there, and so you should know that it exists. If you ever encounter a problem where some sort of statistics are needed that vary with time, then probably it's non-equilibrium stat mech that you need to look at. One of the areas that you will see in the textbook in chapter 17, which we will not cover, so we'll never see it here in this lecture, or in this class formally at least, is diffusion. That's one of the major areas of, it's an example of something called a Markov process. And one of the major Markov processes, at least taken as a whole, are a general whole class of non-equilibrium processes. And diffusion is the simplest among the simplest of the Markov processes. So there is a chapter in this book on something that can be called, that is part of non-equilibrium stat mech, but we won't cover it. But you can look at it on your own, so you can get at least some feeling for at least the very beginnings of one branch of non-EQ stat mech. All right, now we're going to go into kinetics, and a lot of what we're going to do this lecture, pretty much the rest of this lecture, in fact, is stuff that I think you should have seen already in other classes. So I'm going to call this the basics of kinetics. I hope everybody has seen this stuff because I expect that most people have, but also that most people need to be reminded. We're going to go through it, but we're going to go through it quickly, not as in detail and not with as many examples, especially as we would have if this were freshman chemistry or one of the other lower classes on your path to this class. So, the basic things. First of all, definition of what we mean by the rate of reaction. Let's suppose we have some chemical reaction here. I have 3 of them. The formation of water, the hydrolysis of ATP, and then a generic one with 4 reactants and products. What is it that gives us, that tells us, how do we even say what the rate of reaction is? Well, we just look at the rate of change of any of the reactants and products. This is a reactant here for this reaction. The rate of change of a concentration or an activity or a pressure or a mole number or any other, or a mass. There's a whole bunch of different physical quantities you can measure and then take their rate of change, and that can be thought of as a rate of reaction. In this section and in this class, we're going to stick pretty much entirely to this. This is the most common one, that is the rate of change of molar concentration of a reactant or product with respect to time. But be aware, out in the literature, out in the wider world, you'll see these other things, and even other weirder things that are all used as measures and ways of keeping track of the rate of reaction. Yeah, so I say here, usually we use molar concentration, and so for this generic case, there's 2 possible rates of reaction written here, but we could write down any of these ones. We could write out dB dt or dC dt and so on. All of those are possible rates of reaction. In this case, narrowing things down so that we're just talking about molar concentration rather than these other possibilities. But even so, for this generic reaction with 4 species involved, there's 4 different rates of reaction. Take the time derivative, take the rate of change for any of those concentrations, molar concentrations, and they're all rates of reaction. Now, you may say, well, what do I do, Dr. Keller? How do I even know what to say then? Any one of these could all be the rates of reaction. Does that mean there's no single answer to questions in kinetics? And the answer is no, for a variety of reasons, but here's a really good reason. These rates of reaction are oftentimes all related to each other. In other words, there are all these rates, but they're not all independent of each other. Once you know one of them, you can figure out what the other ones are. You can deduce or predict what the other ones are, most of the time, not always. If the reaction in question has no intermediates, so I haven't defined what I mean by an intermediate, and it would be too much of an aside right now to define that well. We'll talk about it later when we talk about elementary reactions. An elementary reaction doesn't have any intermediates, but most reactions are not elementary. So for example, none of these up here, well, I don't know about this generic one, but none of these real ones are elementary. There's intermediates involved. So, well, I guess I can say a little bit here. In the case of this first water-forming reaction, for example, how does the reaction actually proceed on the microscopic scale? Well, what happens is that the H2 molecule, well, this is one model at least for how it happens, the H2 molecule breaks on its own. It's a very rare event, but it does happen, and you get 2 H atoms out. So no longer an H molecule, just 2 loose H atoms. And then the H atom can react with, let's say, an O2 molecule and basically rip an oxygen off of the O2 to form an OH radical and leave behind another loose O atom, and so on. We can go on. Well, all these guys, these H atoms, these OH radicals, these O atoms, they're things that don't appear in the overall reaction here, right? They're not products or reactants. Those are intermediates. And so this reaction has intermediates, and therefore it's not elementary, and therefore the things I'm going to say down below don't apply. This one probably, I mean, I'm not sure, well, I am pretty sure, in fact, that this one also has intermediates. Most overall reactions, if you see some reaction written out like this, probably it's not elementary, probably it has intermediates. The elementary reactions are very simple ones. This is an elementary reaction, by the way. It has no intermediates in and of itself, right? It creates an intermediate for another reaction, but as far as this reaction by itself is concerned, it's simple. It doesn't have any hidden things inside of itself. All right, so if the reaction doesn't have any intermediates, or in other words, if it's elementary, or if the reaction is moving at steady state, in other words, things are just progressing along, it's not building up, it's not decaying down, it's carrying on at a steady way, then in either of those two cases, this set of relationships holds. So this is for AA plus BB goes to CC plus DD. This is for this generic general reaction, minus, because it's a reactant, 1 over the stoichiometric coefficient times the rate of change for A is equal to minus, because it's also a reactant, 1 over the stoichiometric coefficient for B times the rate of change for B. So these two, the rate at which, basically what this is saying is that whenever I use A molecules of A, I've got to also use B molecules of B, and that gives a relationship between these two rates, right? Or between this whole quantity here, right? Minus 1 over A times dA dt, minus 1 over B times dB dt. Both of those are going to be related by the stoichiometry of the reaction. And likewise over here on C, now notice no minus sign because these are products. Reactants get minus signs, products don't. I divide by the stoichiometric coefficient though still, and then I take the rate of change for C, and I can do the same thing for over here for D. The stoichiometry says that all these rates are related to each other. Whenever I lose A molecules of A, I also lose B molecules of B, and I also gain C molecules of C, and I also gain D molecules of D. So all these rates are related. There's all these 4 rates up here, but once I know one of them, I know them all. They're not independent. So I can choose any one of them, and they'll all be just as good. Any one of them will be just as good as any of the others. There are 4 rates, but they're all just fine. So for example, for the 2 real reactions up here, for the water reaction and for the ATP reaction, well, for the water reaction, it's 2H2 plus O2 goes to 2H2O. And so stoichiometric coefficient of 2 for H2, and it's a reactant. So minus 1/2 rate of change for H2. Stoichiometric coefficient of O2 is 1, and it's a reactant, so minus 1 over 1 times rate of change for O2. Likewise, for water, stoichiometric coefficient is 2, and it's a product, so plus 1 over 2 rate of change for H2O. All those rates are related to each other. And for the ATP reaction, I won't go through this one, I guess, but it's the same business. All those rates are related to each other. Again, this applies the vast majority of the time. It's usually assumed that these relationships hold, but strictly speaking, they only hold for elementary reactions or for reactions that are occurring at steady state. So for example, since the water reaction here is not elementary, we know that, this set of relationships only holds if the reaction is proceeding at steady state, which is the vast majority of the time usually in the course of any chemical reaction. If you start a reaction, it ramps up for a little while, then it goes for quite a long time, and then one of the reactants or all of them starts to get used up and it starts to decay away. The vast majority in the middle is the steady state part, and the beginning, the ramp up and the phase down are the not steady state part. These relationships will still work even for this non-elementary reaction in that vast middle part of the reaction. All right. Another way to talk about the rate of change of a chemical reaction is to say this. Let's suppose I have some reaction. Let's say, okay, so this is AA plus BB goes to CC plus DD again. And so I'm looking at one of the reactants here, A, and since it's a reactant, and since I'm assuming the reaction's going forward, the A is going to go away, and I can plot the concentration of A as a function of time. Let's suppose let's suppose A can be measured with an absorption spectrometer, for example, and I just monitor the absorbance of the A as a function of time. And I make a plot of it experimentally. Then the rate of change for that A will be at any one point, right? The rate is changing as time goes by. It's faster here, it's slower down here, and at any one point, it's the slope of this curve, right? The derivative of A with respect to time is the slope of the curve of A as a function of t. And likewise for a product here, in that case, since again the reaction is going forward, the products will be building up rather than going away. But again, if I look at any one point in time, the reaction is going faster here, it's going at some intermediate rate here, and slower here. And you can tell because the slope is greater here, slope's less there, and still less there. So that means the rate is slowing down. And at every point, the rate is, that tangent slope to the curve. All right, now, if the rate is the slope of the curve, that means we're going to be able to derive equations, differential equations, involving time derivatives of concentrations that will allow us to actually solve mathematically for curves like this. We'll see that down below. That's called an integrated rate equation. It amounts to setting up a differential equation, a simple one in our case, and then solving those differential equations. We'll do that for a variety of the simpler and more important and more basic of the chemical mechanisms that exist in chemical kinetics and, well, in the world, in the universe. Next part, topic number 4 among the basics here, is this. We know that the rate of we just said the rate of reaction is the slope as you're moving, as the concentration is changing with time. But intuitively, the rate of reaction should also depend on how concentrated the reactants are. For example, if I have this reaction, 2A goes to A2, so presumably what this means is that 2A molecules were originally free or loose, and they collide with each other, bump into each other, and as a result of that, they get bound, and now you've got an A2 molecule. Well, if that's true, and if the molecules are moving around randomly, then you would expect that when they're densely packed like this, that they're going to collide more often if every collision has some chance of creating an A2 and therefore moving the reaction forward. Then this ought to have a higher rate of reaction than this case over here where the molecules are more spread out and therefore there are fewer collisions per unit time. And that turns out to be true. So here we have dense A molecules, high A concentration, lots of collisions and therefore fast reaction. Over here, more dispersed A, lower A concentration, fewer collisions, and slower reaction. The thing that gives how the rate of reaction depends on concentration, the law that gives that relationship, is called a rate law, not surprisingly, right? And it's usually a power law. It doesn't have to be a power law. We will see examples actually in the enzyme kinetics section that's coming up after this. We'll see lots of examples where it's not a power law, but especially at the basic level like this, it's essentially always assumed to be a power law. And a power law is something like this. You have a rate of reaction over here. You've got something called a rate constant. It's just a pure number for the moment, but we'll spend a lot of time talking about that rate constant later. And I'll say a few more comments about it down below, in fact, right now, or right today. because it's extremely important. It's just a simple thing called K, but it's got a ton of physics buried inside of it. It's where all the action is really for a certain branch of kinetics anyway. So there's a rate constant that's multiplying everything, and then there's a concentration of one of the reactants raised to a certain power, and then there's a concentration of the next reactant raised to a certain power. And if there were 3 reactants, there'd be another one here, so you could have A to the A, B to the B, C to the C, or you can just have one, right? A to the A, and there is no B or C. All those things are possible. How many reactants or products there are varies from reaction to reaction, so all that's fine. But the idea is that everything that's involved, and it's usually reactants, just reactants. Usually products don't appear in these rate laws, though in principle they can. So it's usually reactants. However many reactants there are involved, their concentrations are raised to powers. That's a power law. All right, so a rate constant and some powers, that's what determines the nature of the power law. The power that goes with reactant A is called the order for the rate law in A. The power that goes with reactant B is the reactant for B, the order in B. And then there's an overall order, which is just the sum of the two, the sum of the two powers. So for example, down here, if this is my rate law, just one chemical species, and it's only to the first power, right? There's an implied 1 there. Means that it's first order in A, and it's first order overall, because there's no second exponent. Here's another rate law, which is first order in A, right? And first order in B, but the sum of the two is 2, so it's second order overall. Here's another one, it's half order in A, and it's -1 order in B. Is that possible? Is that allowed? Are negative orders allowed? Are half orders allowed? Yes. In principle, there's no way to rule out absolutely any order at all. Almost always, you will see, especially in this class, that the orders are actually just 1 or 2. It's to see things like this is not exactly rare, but it's relatively unusual. By far, the most common orders are 1 and 2. But these things are perfectly possible. You can't rule them out a priori. So this case then is half order in A, -1 order in B, and minus half order overall, adding them together, right? So there's no limit, and don't be shy about talking about half orders, or, I mean, I say here that you can have orders of pi, or the square root of 2, or 1/3, or 1, or 0, right? If I put a 0 here, A to the 0 power, B to the 1, well, A to the 0 power is always a 1, right? So that's just basically saying A isn't in there at all. That's perfectly fine. That means it's 0 order in A. Perfectly fine. That means it's kind of, I mean, in a formal sense anyway, every rate law is 0 order in everything that doesn't appear. That's perfectly fine. It's a little bit not useful, but it's totally true. All right. Okay, so that's the rate law. We've talked about the powers a little bit. What about the rate constant? I already sort of built that up a little bit. It's important. It's going to get talked about. Actually, the whole latter section of this kinetic section is going to be talking about theories for the rate constant, because all the molecular information is buried in that rate constant, right? If I show you this rate law, you can't tell what reaction that's for. You can tell that there's this reactant and that reactant present, but you're not even sure they're reactants, right? You just know those chemical species must be in the reaction somewhere, but you can't tell anything else about what that reaction is. You can't tell its stoichiometry. You can't tell what's being created or destroyed. You can't tell whether there's other things there or not. All that information about the nature of the reactants and products is buried in K here. That K is hiding an enormous amount of complication. And for our purposes for the moment, that's good, right? That makes things simpler for the moment. Later, we're going to have to understand some of that complication at least, but we won't go very far. People have spent their lives trying to understand rate constants, and we won't go anywhere near all that. But we will have to go a little ways just to get at least some basic ideas. Probably, people know we're going to talk about Arrhenius theory. That name should sound familiar. and that's part of the rate constant theory. People who have freshman chemistry here, at least at UNM, know about Arrhenius theory. We'll also talk about I-ring theory. I'll talk about these things below, transition state theory, Cramer's theory. There's a bunch of different rate constant theories, and we won't talk about many of them, but we will talk about I-ring and Arrhenius. So those are coming. But all the molecular details is hidden inside that K. It's the only way to tell one reaction from another, right? The only difference between this if I have A plus B goes to C, and I have 2A plus 3B goes to C, goes to D, let's say. Those are two different chemical reactions, right? They have the same reactants, but they're two different chemical reactions, different products, in fact. Both of those, either of these, could have this as its rate law. How do you know one is different from the other? Well, they will have different rate constants. The rate constants depend on all this molecular detail, and therefore they'll be different for those two reactions. But that's the only way you can tell, at least by looking at the rate law. All right, another thing to say, that the rate constant itself isn't really a single physical quantity. It's kind of a phenomenological parameter that gets put into chemical kinetics. And one of the manifestations of the fact that it's really not a single universal physical quantity is that its units change depending on the nature, depending on the overall order of the reaction. So let's consider this rate law, K times A. That's a first order in A, and first order overall, right? Also, so this is a first order reaction, no matter how you look at it. In that case, let's look at what the units on K have to be. Over here on the rate side, it has to be molar per second, right? Rate of change of concentration per time. So molar per unit time per second. Here we have concentration of A, and that's going to be in molar units, which means that to make these two sides consistent with each other, this rate constant has to have units of 1 over S. So for a first order reaction, the rate constant has units of 1 over S. And in fact, or S to the minus 1 as it's often written. And in fact, that's one way to identify an overall reaction, even if, or a first order reaction. Even if I didn't have this rate law, if somebody gave me a rate constant and told me that its units were seconds to the minus 1, I would know instantly that it was a first order reaction. This is the only reaction that has these units, for which K has these units. All right, here's another case, but this one's overall second order, right? It's first order in A and it's first order in B, but it's second order overall. And what does that mean? Well, molar per second on this side again, but 2 molar factors on this side, right? It's really molar squared for just these concentration terms here. And that means that in order to make the units match on both sides, again, this K has to have units of 1 over molar and 1 over seconds, or molar to the minus 1, seconds to the minus 1. And that's true for every second order reaction. So for example, if I write rate is equal to Ka squared, right? That's a second order reaction too. It's now second order in A all by itself, and there is no B, but it's still second order overall. This rate constant will be have the same units as that rate constant. Second order overall always has these units. And so again, if I'm given a rate constant and the guy who gives it to me tells me it has these units, I know it's a second order reaction. Here's a weirder case. It's half order in A and first order in B. That means overall it's 3/2 order, right? It's 1.5 order. Perfectly possible. In that case, again, molar per second on this side, and molar to the 3/2 power on this side, which means that K, in order to make things match, has to have units of 1 over molar to the half power, the square root of molar, times seconds, or molar to the minus 1/2 seconds to the minus 1. And again, this is now a 3/2 order reaction. This is unusual. I mean, it does happen, but it is unusual. But if you ever encounter a 3/2 order reaction in your future life, then you know that its rate constant's got to have these units. And again, if somebody gives you a rate constant with these units, you know that it's a 3/2 order rate law. All right, I said all this stuff before, but it doesn't hurt to reiterate it once more. We will learn much more about K in the stuff that comes later, and that comes under the heading or title of Arrhenius theory, Eyring theory. Transition state theory we won't talk about very much. We'll talk about it really as a special case of Eyring theory, though it is a much more complicated and powerful thing in its own right. And we won't talk about Cramer's theory. That's also a very powerful rate constant theory. We'll mostly just talk, I think we'll entirely just talk about these first two, but that's enough to get us started. All right, topic number 7. How do we actually go about finding a rate law? Let's suppose we've got a chemical reaction. Here's our chemical reaction in this case. Glucose plus ATP goes to products, and we don't care what the products are right now. It goes to a complicated product. I think it's, what is it? It's glucose 6-phosphate is what it goes to. In fact, it's catalyzed by hexokinase, an enzyme, but we don't need to know the products because it turns out that the rate law only depends on the reactants in this case. That's common. In fact, it's the usual case. And so we assume that the rate is of this form, rate constant, glucose to the A power, ATP to the B power. But we don't know what this rate law is. In order to know what the rate law is, we've got to know what this A is, what this B is, and what this K is. And so these three things, finding these three things, amount to finding what the rate law is. In fact, if you take some data and you find out that you can't get consistent results by trying to find an A and a B and a K, then you know that your rate law to start with was of the wrong form, and you've got to pick a different form, something more complicated maybe. All right, so let's do an example. Let's consider that we have some experimental data, and this is not real data, it's made up data, but let's suppose it's experimental data. And so we have glucose concentration here in this column, ATP in this concentration in this column, and then the third column gives what's called the initial rate. That means we start the reaction off, we measure how fast the concentrations are changing, in this case in units of millimolars per second, and then we stop the reaction because all we cared about was how fast it was going right at the beginning. In fact, we don't want the concentrations to have time to change appreciably, so that's what it is meant by initial rate. You start the reaction off, measure it right away, and then stop it. And then you change the concentration. So if in this first line we started with 1 millimolar glucose and 2.5 millimolar ATP, and we got a 5 millimolar per second rate, next we do another experiment now, and we change the concentrations of the glucose. Now it's 3 millimolar. ATP concentration, notice, hasn't changed though. We kept it the same. Why? Because it's generally a good rule to only change one thing at a time. Don't go changing 3 things at once, and don't even change 2 things at once. So we kept the ATP concentration the same, but we changed the glucose concentration. And when we did that, we make the measurement, we get 15 millimolar per second. Now, if you're quick, you'll notice, okay, we increased the glucose concentration by a factor of 3, and lo and behold, the rate went up by a factor of 3. What does that suggest? It suggests first order, right? The rate is proportional to the glucose concentration. And so you can kind of see it. You can just read it right off the data because this is a particularly simple special case. But what happens if it weren't so simple? Well, I'll show the general procedure for finding the rate, the powers, the rate, the orders, even when things aren't so obvious in this as this. All right, now for line number 3, we go back to the original glucose concentration, right? Between here and here, we also haven't changed the glucose concentration, so we're sticking with the same idea. We're changing the ATP concentration. We increased it by a factor of 4 here. But we didn't change, between these two lines, we didn't change the glucose concentration. So we're, again, changing just one thing at a time, keeping all the other stuff constant. And comparing line 3 and line 1, we see again that the rate increased also by a factor of 4. And so we also right away can, by inspection in this case, tell that it's first order in ATP also, right? It's first order in glucose, it's first order in ATP. As we're changing these concentrations, you can think of that as ways of probing what the order is for glucose. In this case, when we're changing the glucose concentration, and in this case, when we make a change, we're probing what the order is in ATP. All right, so we can see the answers in this case, but you won't always be able to see the answers. How do we go about it more systematically? Here's the general case. We need to get the powers first. Later we'll get the rate constant too, but we need to get the powers first, so we need to analyze this expression. Because there are powers involved, one way that should suggest always when there are powers involved is take logs. So we take the logs of both sides of this thing, and if we use the properties of logs, then we find that the logarithm of r, and we're using natural logs, but if we were using log base 10, we'd get the same results. So natural log of r is equal to the natural log of k plus a times the natural log of a plus b times the natural log of b. That's just taking the log of that on both sides. And now that has to apply no matter which row of data, which experiment we're thinking of. So it has to apply when the rate is the rate from row 1, and the concentrations are also the A and B concentrations from row 1. It also has to apply when it's from row 2 or from row 3, but row 1 and row 2 are enough for us to get there for now. So we've got these two relationships. One basically holds for row 1, the other one holds for row 2. Let's subtract these two relationships from each other. Actually, I'm going to subtract this guy from that guy. And when I do that, I'm going to get the log of R2, rate for row 2, over the rate for row 1. In other words, by what factor did the rate change in going from row 1 to row 2? That has to equal the power for A, the order for A, times the logarithm of the ratio of the concentrations for A for row 2 and row 1, and likewise the power for B and the ratio of the log of the ratio of concentrations for B. Now, that's fine, that's a good relationship, but in fact, in row 1 and row 2 up here, the A concentration didn't change, right? We deliberately kept it constant, and we only changed the B concentration, which means that this A over A2 over A1, that's a 1. And the log of a 1 is a 0, so that term goes away for rows 1 and row 2. And that means that we really just have this log of the ratio for rows 1 and 2. Sorry, that should be B there. Let me fix that. Let me make sure I'm doing this right. Yeah, it's ATP that's... Oh, no, I take it back. I had it right to start with, sorry. ATP is B, so it really is glucose, which is A in this case. All right, so I'm sorry. It's not this term that goes away. I made a mess of this, so I'm sorry. It's not this one that goes away. It's not A that's 1, it's B that's 1. It's B that doesn't change, right? ATP is B here. So it's B that doesn't change, so it's, let's get my pink back. That's the one that goes to 0. And yes, this was the right relationship to begin with. I did it right the first time. And that means we can solve for A. So A is equal to the log of the ratio of the two rates over the log of the ratio of the two concentrations. For in this case, A is glucose. And if we now do the opposite, right, if we take instead of rows 1 and 2, if we consider rows 1 and 3, then the glucose concentration is the same for those two rows, and the ATP concentration has changed for those two rows. So doing the same thing, we get the B power, and that's the log of ratios for, that should be 3. I did make a mistake here, yeah. Okay. So that's the ratio of 3 to 1, rates of 3 to 1 over ratio of concentrations of B3 over B1. All right, so that's the general formulas, and if there were more products or more reactants involved in the rate law, it would be more complicated. You have more rows. but the idea would be the same. So for this particular case, we have A is equal to the rates for rho 2 over 1 over the glucose concentrations for 2 and 1. That's 15 over 5 on top, which is log of 3, right? And 3 over 1, which is also log of 3, which means we got the same thing top and bottom, which means we got a 1. So we are indeed getting a power of 1, which we knew already to be right. So we didn't really need all of this complication in this particular case, but in more complicated cases we would have. And now the same thing using rows 1 and 3 gives us also a power, an order of 1 for B, for the power for ATP. And so overall, our rate law is some K that we still don't know, times glucose to the first power, times ATP to the first power. How do we get K? Well, now we can use any of the rows. We've got 3 different rows, and they all have to have the same K. Where we are, here we are. So we just take the data from one of the rows, and it doesn't matter which one. It shouldn't matter which one. If it does matter, then we made some mistake someplace. Well, if it doesn't matter within error, within round-off error, then we made a mistake. But if everything is good, then we can use row 1, which is what I've used down below, but we could use row 2 or row 3. If we use row 1, then we can say that the rate is solving for the rate constant in this, right? Then the rate constant is the rate over the 2 concentrations. We know the powers now, right? So we know we can fill in here. And that's 5 millimolar per second over 1 millimolar for glucose, 2.5 millimolar for ATP, and that gives us 2.0. And now note the units, millimolar to the minus 1, seconds to the minus 1, right? Because this is a second order reaction overall. So we should get molar to the minus 1, seconds to the minus 1, but we used millimolar concentrations all the way through, and that gave us millimolar instead of molar, but it's the same thing. All right, that is, I think, enough for today. I will stop there, and we'll talk about integrated rate laws, which involves solving some differential equations next time.